Welcome everyone to this section of the course on NumPy. In this lecture, we're going to give you an overview of what we're going to cover, as well as give you a basic brief overview and introduction to the NumPy library. So as mentioned, this is going to focus on just a quick crash course on NumPy basics. We're going to cover the following topics. What is NumPy? Why we use NumPy? Then we'll talk about actually using NumPy arrays and matrices, how to index and slice information or elements out of those arrays or matrices, various NumPy operations. So what actually is NumPy? NumPy stands for Numerical Python, and it's an open source numerical library used for working with mathematical functions of multidimensional array and matrix data structures. It's already installed in our environment, and it's actually a very common library used in data science and machine learning. So why would we actually want to use NumPy? We mentioned that we're going to be learning how to use NumPy arrays and matrices. But if you're already familiar with Python, then you know that Python actually has a built-in list structure that can act as an array. So why do we actually need NumPy instead of just using the core Python list? Well, NumPy arrays use less memory than a normal Python list. NumPy can also read in information faster than normal Python. It has lots of convenient broadcasting operations that can be performed across array dimensions. So as we learn more about NumPy arrays, we'll begin to see capabilities that they have that a normal Python list doesn't. Okay, let's go ahead and get started. I'll see you at the next lecture. Welcome back. In this lecture, we're going to be discussing the very basics of a NumPy array, which is our main data structure when working with NumPy and data sets in general. So let's talk about how to create arrays. We'll discuss how to convert existing objects to a NumPy array, such as a normal Python list to a NumPy array. Then, we'll show you some built-in NumPy functions to quickly generate useful arrays. Then we'll talk about creating arrays and matrices of random values. Often in data science and machine learning, we need to quickly create random values in a certain shape, and NumPy has a lot of tools for that. Then, we'll talk about some very basic array attributes, such as data types and shapes. Let's get started. Okay, here I am at my Jupyter notebook. To begin using NumPy, we want to import it. So we will say import NumPy, and then by convention, we import NumPy as NP. Be careful with the spelling of NumPy. Sometimes students get confused with capital N's and capital P's. Everything here should just be lowercase. The stylized convention of capitalizing the N and the P is just for stylizing in the actual naming of the library for things like documentation. But when we import it, we're just going to import NumPy as NP. Let's first discuss how we actually create a NumPy array. So NumPy arrays are essentially the main way we're going to be using NumPy throughout this course. Now, as discussed, we can have a normal Python list. And here I can create one, just my list, 1, 2, 3. And if I want to have this or cast it as a NumPy array, I can call the function NP array and then pass in my list object. And you'll notice now when it's displayed, it denotes that it's a NumPy array by having array at the front of this. I can also do the same with a nested list. So let's go ahead and say nested list is equal to, and I'm going to create a list of lists. So we'll have 1, 2 as the first object there, then 3, 4, and then 5, 6. So notice here, if I were to ask for my nested list back and just run this, I just get back this list. But if I were to then transform this into a NumPy array, NumPy will actually begin to keep in mind the shape of what's being passed in. And it's going to format this as what is essentially a 2D matrix of 3 rows by 2 columns. And we can see the actual dimensions here by the number of brackets or braces at the beginning and at the end. So this essentially indicates we're dealing with a 2-dimensional object. Now, typically, we're not going to be just transforming normal Python objects to a NumPy array. Instead, there's lots of useful built-in ways to generate arrays. So let's cover a few of those. One way is to use NP arrange, which is similar to NumPy's built-in range function. So we can say NP arrange, it only has one R here. And then what we can do is if you do Shift Tab, it'll tell you how it works. Essentially the same way as Python's built-in range object, where you have a starting point, a stopping point, and then an optional step size. So for example, if we wanted all the integers between 0 and then up to, but not including 10, we can say 0, 10. And that will give us, starting at 10, go all the way up to, but not including 10. So we see the numbers 0 all the way to 9 here. So keep that in mind. This stopping point is up to, but not including it. Then we can also have an optional step size. So by default, the step size is 1. So just go from one integer to the next in a step size of 1. But I can change this to be a step size of 2, which is kind of a quick way to get all the even numbers. So it can be 0, 2, 4, 6, 8. And if for some reason I wanted to continue past this and actually get 10 in there, then I would say go up to, but not including 11, rerun this, and now it includes 10. So we have our starting point, our stopping point, which goes up to, but not including the stop point, and an optional step size parameter. Next, often is the case in data science and machine learning that we want to quickly create arrays of just a bunch of zeros or ones. And to do this, again, NumPy has a built-in convenience function called zeros. And zeros, if you just pass in one number, such as 3, returns a vector of 3 zeros. Something to keep in mind here is you'll notice that it says 0 point, which essentially indicates that these zeros are floating point numbers. And often when you're working with NumPy, and then later on we'll learn about pandas, things are going to be automatically converted to floating point precision numbers instead of being kept as integers. One of the few techniques we're going to be learning about for keeping things in integers is this NP range. Pretty much all the other functions we learn about will convert things to floating point numbers. So we have NP zeros. If you pass in a single number, it gives you kind of this 1D vector of just those 3 zeros. But you can also say NP zeros and then pass in a shape. So if we do Shift Tab here, notice that it'll say, what's the shape you want? So it can say something like, give me a 4x4 matrix. And here we have, again, 4 rows by 4 columns, all of zeros. Or I can begin to edit this. And we'll see that the second dimension, so if I say 4x10, lines up with the number of columns. So it's how many rows you want by how many columns you want. So here we have 4 rows of 10 columns of all zeros. And if you really want these zeros to be integers, you can begin to edit this data type parameter. So you can say dtype is equal to int if you really wanted these to be integers. For pretty much all our use cases, we won't really have to worry about integers versus floating point numbers. So we'll close that out. So we know NP zeros, and similarly, there's NP ones, which is just NP ones. And you can say NP ones 3, which gives you a 1D vector of just a bunch of ones. Or you can also pass in a shape, such as 4x4. And there's my 4x4. Notice the sets of double parentheses here. This is essentially indicating that I'm passing in, as my first argument, a parameter of a tuple. And then these outside parentheses are for the actual function call itself. Next, we have linspace, which is a useful function which returns evenly spaced numbers over a specified interval. Not to be confused with what NP Arrange is doing, which is setting a starting point, a stopping point, and then taking some arbitrary step size. NP linspace, instead, the way it works is we say NP linspace, we give it a starting point and a stopping point, but then we ask for the number of actual elements we want evenly spaced between those 2 points. So I can say 3 here, run this, and then it'll return back 0, 5, 10. So these are 3 points, including 0 and 10, including that starting point and the stopping point, and it's 3 points evenly spaced because in between the 0 and 5 is 5, and in between 5 and 10, well, it's evenly spaced to also be 5. If we ask for more, so for example, let's go ahead and ask for something like 21 evenly spaced points. We run that, and now we get back 21 elements, going from 0 to 10, where the even spacing is 0.5. So to go from 0.5 to 1 to 1.5, etc. Now, something to note here is that linearly spaced calls actually include that stop value. So to obtain an array of what you may refer to as common fractions, you may need to increase the number of items requested. So often beginners sometimes just go 0 to 10, give me 20 evenly spaced points, and they get these sort of weird fraction calls or weird decimal places. Because we're including the stop value, we may need to do something like increasing the number of items requested to 21 in order to see these common fractions. So just keep that in mind of NP linspace. That's because it's actually including the stopping point this time. Now there's also the capability to create an identity matrix. An identity matrix is simply a matrix of all zeros with a 1 along the diagonal. So for example, if we say np.I of 5, it gives us a square 5 by 5 matrix with 1s along the diagonal. And this is really useful for a lot of linear algebra tasks. The reason we only need to provide one number is because, by definition, an identity matrix is always square. Okay, so those are a couple of built-in functions in NumPy. Finally, let's show you how to create random arrays. So there's lots of different functionalities with random. And the way we do this is we say np.random dot, and if you were to hit tab here, you would notice that there's actually a bunch of different random function calls that NumPy has available to us. So many types of random distributions we can call from. So what we're going to do is just show you a couple of very basic ones. There's np.random.rand, and if you ever are confused over what actual random distribution is returned, you can simply do Shift-Tab in the Jupyter Notebook, expand the documentation, and it will report back to you how it's actually grabbing that distribution of random numbers. So in this case, just the call of RAND or rand grabs random values from a uniform distribution, meaning everything has the same likelihood of being picked from 0 to 1. So we'll go ahead and ask for instance, 2 random numbers. And that will give you 2 random numbers with a uniform distribution between 0 and 1. And every time you keep running this cell, notice you'll get back different random numbers, all between 0 and 1. Now, let's say you actually wanted a matrix. So the way this works is you say np_random.rand, and then instead of passing a tuple for this one, what you can do is pass in 2 parameters. Let's say 3 rows by 4 columns. Run that, and now we have 3 rows by 4 columns, all of random numbers between 0 and 1, where all the numbers between 0 and 1 have the same likelihood of being picked. Okay, so that was with a uniform distribution, but there's also the capability to grab it from a standard normal distribution. And for that, we say np_random.randn. So randn is doing the same thing from a standard normal distribution. A standard normal distribution essentially just means that the mean is 0 and the variance is 1. So that will actually allow us to then get some negative numbers if we do this. So let's say I wanted 5 by 5, run this, and here we have some negative numbers, and this is a standard normal distribution. It's centered around 0 with a variance of 1. Okay, so we can actually grab random integers by saying np.random.randint, and the way this works is we provide a low and a high, and then optionally we can request a size. Keep in mind the low is inclusive, meaning the low has a chance of being picked, and the high is exclusive, so the high will not have a chance of being picked. So let's go ahead and say we wanted to actually make some random values to try to simulate people's ages. So we could say something like from 1 to 100, go ahead and give me a random number. And this is one way we could then generate random ages. So this person then is 56 years old. And let's say we wanted to quickly generate 10 random ages. The second parameter is just how many we want. So we can ask for 10, and there's our 1D vector. Keep in mind, there's actually a size requested. So we could say something like, give me 2 by 3 as a tuple, run that, and it would kind of structure it out that way. 2 rows by 3 columns. So that is randint. Now you may be wondering, what if I actually want to do some sort of random numbers but have reproducibility? So every time I run this notebook or run this piece of code, I end up generating the same random numbers. Well, that's where a random seed can come into use. So what I'm going to show you is np.random.seed. And the seed allows you to just pass forth an arbitrary number choice. So the actual number choice isn't that important. The fact that's important is that you choose the same number every time. So let's say I want you to generate the same random numbers on your computer that I'm about to generate on mine. What we can do is choose the same seed value. So I'll choose the seed value of 42, and you can go ahead and type that in. And in the same cell, let's go ahead and say np.random.rand, and then just, let's say I want 4 random numbers. We run this, and if you ran this the exact same way I did with the seed call and the random call in the same cell, then you should see the exact same 4 random numbers. This is going to be really important later on in the course because while we do want some elements of randomness in many of our functions in data science and machine learning, such as a random test train split, we want to make sure, for reproducibility's sake, that your random splits and random values are going to be the same as I show in this notebook. And in order to do that, we'll be using this seed. Now, a question I often get from students is, what's the meaning of this number 42? And it's basically just the arbitrary choice you use to seed what's known as a Mersenne twister, which is a way of generating these kind of pseudo-random values. You can check out the reference link in the notebook for more information on that seed. But in our use cases, basically, we're just going to be using the same seed values as our choice. Now, something to keep in mind is if I grab np_random.rand and then ask for this in another cell, rerun this, I will get now a different set of values than what I did up here. And that's because this is the second call after setting my seed. However, if I keep running these two, they'll always give me the same random values. So often what I would say is try to make sure that your generation of the random numbers is occurring in the same cell as your actual seed value. That way you don't accidentally run this cell multiple times. And you can see here on the 5th one, it's going to give you something different. On the 6th one, it's going to give you something different, etc. So keep that in mind. If you ever want to reset your seed, just go ahead and run that, and then we'll kind of repeat that cycle. Okay, so that's the seed. Finally, I want to show you just a couple of useful array attributes and methods. So often what we can do is we can reshape a 1D vector to any matrix shape we want. So let me go ahead and create an array. We'll do this by saying np_arrange 25. Go ahead and run this. And I'm also going to create an array of random values. So we'll say ran array is equal to np random.rand int. And this will go from 0 to 50. Let's go ahead and just say 10 here. So here's my normal array, which is just the numbers 0 through 24. And my random array are going to be these numbers right here. Keep in mind, depending on how you set your seed right now, you may have different random values than I do, but that's not important for this particular part of the lecture. Okay, so let's say I wanted to reshape this array. When you create a 1D vector, you can ask for dot shape. So let me actually show you that in a new cell. I'm going to say array dot shape. And you'll notice that right now, it only has one dimension defined. It just says this is essentially 25 numbers. What I can do is I can reshape this by saying R or ARR, reshape, and I can reshape this to be 5 rows by 5 columns. Run that, and now I've taken my original array and reshaped it to be 5 by 5. Something to note is this doesn't actually affect the original object permanently. If I ask for array again, I still get back the original. If I wanted this to be permanent, I could simply just reassign it to array is equal to array.reshape. And here we can see the 5 by 5. Some other things to keep in mind here is that you're not going to be able to reshape the array into a set of dimensions that doesn't make sense. Right now, this is 5 rows by 5 columns, which means I have 25 elements total. If I were to try to reshape that into something like 3 by 6, which would only be able to contain 18 elements, you will get an error. And it'll basically say, I cannot reshape something of size 25 into a shape of 3 by 6 because there's only space for 18 elements, and here we have 25. So keep that in mind if you ever see that error with the reshape call. Finally, I want to show you the min-max and argmax and argmin parameters or attributes. So we can take our random array. Here it is. And let's say I wanted to figure out what the max value of my array was. I'll go ahead and just say off of this dot max, open and close parentheses, and I'll return back the max value in the array, which happens to be 43 in my case. Now let's say I was actually interested in the location or index location of that max value. The way that works is I say arg max, run that, and that will give me back the index location. So the index, just like a normal Python list, starting at 0. So 0, 1, 2, 3, 4, 5, 6, 7, and there's the max value of 43. Similarly, we can do the same with min, so I can ask for the minimum value, which is 1, and I can also ask for the minimum value location, which in this case is occurring at index 5. And finally, there is the data type attribute. You can also grab the data type in the array. So I can say something like ran r dtype, run that, and it'll report back this is a 32-bit integer. Or if I were to check some of my other ones, for instance, let's go ahead and set this. I'm just going to copy and paste this random array here. So my array, run that. We can see here that these look to be some sort of floating point. I can always check that by saying, what's my data type or D type? Notice I don't have open and close parentheses here because that's actually an attribute. And it'll tell me that these are 64 floating bit numbers. Okay, that's the very basics of NumPy arrays, generating NumPy arrays, both built-in functions and random values, as well as things like shape, reshape, and data type. Thanks, and we'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to talk about indexing and selection in NumPy. Specifically, we'll first talk about grabbing a single element, then expand this to grabbing a slice of elements. Then we'll talk about broadcasting those selections, indexing and selection in 2 dimensions, and then we'll talk about a very important topic called conditional selection, which we will also see a lot in pandas and dealing with data and data cleaning in general. Let's head back to the notebook and get started. Alright, in my notebook, I've already gone ahead and imported NumPy as NP. Next, what I'm going to do is just create a simple array by saying NP arrange from 0 to 11 with a default step size of 1. So I have numbers 0 through 10. Now let's imagine I wanted to just select a single value. To do this, I simply pass in the index, just as I would select a single value from a normal Python list. So if I just say 8, it grabs whatever is at index 8. So there we have the value 8. Let's imagine I wanted to get values in a range. I can do that the exact same way I can do this with a normal Python list, with a starting position, a colon, and then an ending position, which will go up to but not including. So for example, if I say 1:5, it goes up to but not including 5, starting at 1. So I get the numbers 1, 2, 3, 4. If I want to start at the very beginning, I can either say go from 0 up to but not including 5, or I can omit that 0 and say colon 5, which will basically say start at the beginning and then go up to 5. So these 2 cells are essentially the same thing. It's up to you whether or not you want to include that 0. Similarly, to go all the way to the end from a starting position, you can say starting at index 5, colon, and it will go all the way to the end. This is nice because that way you don't need to actually know how long your array is to index all the way to the end. Now, let's quickly discuss broadcasting. NumPy arrays differ from normal Python lists because of this ability to broadcast. With lists in normal Python, you can only reassign parts of a list with new parts of the same shape and size, and then you would also need to then possibly reassign this to a new variable. However, NumPy, you can actually broadcast a single value across a larger set of values. Let me show you what I mean by that. Let's take a look at our original array, the numbers 0 through 10, and then what we're going to say here is grab all the numbers from 0 to 5 and set that equal to 100. You would not be able to do this with a normal Python list. If you take a look at our array, notice now it's been changed. The values in the sections from 0 to 5 have this broadcasting reassignment. So 100 has been broadcasted across these values. Let's go ahead and reset this by saying NP arrange 0 to 11. The next thing I want to point out is actually slicing a section in an array and setting it to a new variable will actually only act as a pointer to the original array. So I'm going to say slice of array is equal to my array from 0 to 5. So if I check out that slice of the array, then I get 0, 1, 2, 3, 4. And if I take a look at my original array, it's been reset so that it's 0 through 10. Now let's imagine I grab this slice of the array and I say just the colon to select everything. And I set that equal to 99. So now if I take a look at the slice of my array, everything has been set to 99 because I just set a colon here, which basically means from beginning all the way to the end. Now what do you think is going to happen with my original array? Well, with NumPy, that slice of the array was actually, when you assigned it here as array 0 through 5, you're basically just pointing it to the original array, which means this broadcasting operation has actually affected the original array. If you wanted to not have it affect the original array, you would need to explicitly set a copy. So you have to do something like this. Array copy is equal to whatever original array, and then you call the copy method off the original array. And that way, you can do any sorts of changes you want to this array copy, such as grabbing everything and setting it equal to 100. And if you take a look at my array copy, that is now all 100s, but my original array hasn't been changed because of specifying that dot copy. Okay, so we talked about indexing and selection across just a one-dimensional vector here. We also talked about broadcasting. Next, what I want to talk about quickly is indexing on 2D arrays or matrices, and then we'll talk about conditional selection, which is a very important topic. To begin, let's go ahead and create a two-dimensional array. We'll say array 2D is equal to NP array. And here what I'm going to do is simply kind of cast as quickly as a list by saying 5, 10, 15 as the first item in this list. Then we'll create another one, 20, 25, 30, and then finally 35, 40, and 45. So note here, what I essentially have here is a list of 3 lists. I'm going to transform that into a NumPy array of NP array, and that will be my two-dimensional array. So now if I take a look at array 2D, I have this. So let's imagine that we actually wanted to just grab a single row. Well, indexing is basically going to work the exact same way in 2D, except now you have a dimension for the rows and a dimension for the columns. The first one is the rows. So if I say array 2D dot shape, this returns back the number of rows first and then the number of columns. So at index 0 we have number of rows, at index 1 we have number of columns. That distinction is going to be important later on when we cover pandas. So let's imagine I wanted to just grab from array 2D a single row. Then I can pass in an index, so for example 0, and that will return back that very first row at index 0. If I wanted to grab the last row, well, for example, that's at index 2 because we're starting at 0. So that returns 35, 40, 45. Now let's imagine I want to grab a single element value from somewhere in one of these rows. Well, notice now I have this array, so I can index off that row array. So let's imagine I wanted 25. Well, that's at row 1, and then I could either index off of it with 2 bracket notation to then also say 1 to get 25, or what's more common is to just put this in the same set of brackets separated by a comma. So 1, 1 says at row 1, column 1. So let's go ahead and pick another number just to make sure we understand, like 15. That's in row 0 at column 2. We run that, and then we get back 15. Now we can also do the same thing, except expand this to slicing. For example, let's say we wanted to slice this little square of 10, 15 along with 25, 30. The way we could do that is simply by thinking of what rows we wanted first. So I want rows 0, 1, up to, but not including, at index 2. So I can say for my rows, go ahead and give me colon 2, which if we think about this, returns back rows 0 and 1, so up to, not including 2. Now let's imagine I only wanted 10 and 15, 25 and 30 from that. I could then say comma, and say something like starting at column 1, or column at index 1, which is 10, 25, go ahead and colon, go all the way to the end. And here we can see how we could grab that little subsection of our matrix. Now don't worry too much if you get confused by this sort of double notation. We really won't see this that often with real data sets. With real data sets, the rows stand for data points and the columns typically stand for features, so it's unlikely we need to do some sort of double subset. Typically, we're either subsetting just on rows or on columns. It's quite unusual to do something like this, but you should be aware of that sort of notation in case it does come up. Finally, the much more common type of selection we'll be doing is called conditional selection. For this, we'll go ahead and show you an example. We'll say NP arrange 1 to 11, and here's my array 1, 2, 3, all the way to 10. Now what I can do is I can actually broadcast a condition or a comparison off of this. So I can ask for, where is my array greater than the number 4? So I run that, and this returns back a NumPy array of Boolean values, where the index location matches up with the original data. So you notice it says false, 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 and then once it gets to 5, it suddenly becomes true, true, true. So what I could do is, showing you this in multiple steps, I could say my Boolean array is equal to array greater than 4, run that, and now I have this Boolean array, and I could use this to filter. So I could pass that in to my original array, run that, and now it will only return back the index locations of this Boolean array where it happens to be true, which is 5, 6, 7, 8, 9, 10, since these are all greater than 4. So again, the steps here I did was have some sort of original array, do a comparison operator, which gives you back this Boolean array, which you can then use to filter out your original array. Now I separated this out into multiple steps, but theoretically we didn't actually have to do this reassignment. So typically what we see is this sort of notation. We take our array, and then we ask for some sort of comparison, such as array greater than 4. Run that, and then we see here 5, 6, 7, 8, 9, 10. So this is the sort of thing we're going to be seeing quite often, especially when we move on to pandas. And pandas, we'll later learn, will give us the ability to then do something like multiple comparisons. So for right now, we just need to understand this basic idea that I can perform a comparison within my array and then pass that as my conditional selection filter. Later on, we'll discover more complex ways in order to do this for even more functionality. But for right now, we've discovered how we can actually index and select off one-dimensional arrays. We've talked about broadcasting, and we talked about indexing and selection on two-dimensional arrays, and finally, this important topic of conditional selection. Thanks, and we'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to be talking about NumPy operations. We'll discuss various arithmetic operations as well as some universal array functions and summary statistics you can use with NumPy. These sort of operations will easily extend to pandas as well. Let's get started. Alright, now I've already imported NumPy as NP. The next thing I'm going to do is set array equal to NP arrange 0 to 10, and let's check out this classic array. Now let's quickly talk about arithmetic between arrays, as well as arithmetic between a scalar with an array. If I were to take this array and say plus 5, what's going to happen is NumPy will perform this operation on an element by element basis. So it will take every number in that array and simply add 5 to it. And the same goes for any major function. So for example, array minus 2, etc. It all happens on an element by element basis. Now, the same thing happens when we take an array and do an operation against another array. Keep in mind, these arrays have to be the same shape in order for this to work. So, if I were to take my original array and add it to itself, I've essentially doubled every number in the array. And keep in mind, what's going to happen is I can do this for any sort of operation. Multiplication, division, etc. So if subtraction, everything goes to 0. Something I want to point out is NumPy is a little bit special in the way it deals with divisions by 0, or with something like a division error. So what actually happens is you get a warning instead of a full error. For example, if we take a look at my original array, I have 0 as one of the options. So if I were to say my array divided by itself, I'm going to end up getting, at the very first index location, 0 divided by 0. Technically, mathematically speaking, this doesn't really actually make sense. But if I run this, notice NumPy will still output a result. However, it will give you a warning that some sort of invalid value was encountered during division. So what it does here is it replaces 0 with, or 0 divided by 0 with this nan or not a number. What's also interesting is if I were to try to do 1 divided by 0 in normal Python, I will get a 0 division error, division by 0. However, if this occurs within NumPy, so if I do 1 divided by an array, essentially taking the reciprocal of every number in this array, at the very first element, I would get 1 divided by 0. So normal Python won't let you do that, but if you have NumPy, what's going to happen is it will also report back, again, a warning, divided by 0 encountered in true divide, but it has a sort of placeholder with divided by 0 by saying this infinity. So keep in mind, if you have 0 being divided by something, such as 0, we'll end up getting not a number. If you have some sort of element or scalar being divided by 0, then we'll have this placeholder of infinity there. The main thing to notice here is that NumPy won't give you back a full error. It will only give you back warnings, and it will still actually output a result. This could be dangerous because often we would expect our program to crash or have an error when NumPy will kind of keep chugging along, replacing this with either nan or infinities. It's just something to keep in mind. Now, NumPy also comes with many universal array functions. So we saw the basic ones that are built into Python, like arithmetic and division, but there's other things that we can easily call on every element in this array. For example, I could say NP sqrt for the square root, and we can see here we've taken the square root of every number in that array. And I can do things also like trigonometric functions. So take the sine of every number in that array, or take the log of every number in that array. And same thing here, we start getting errors if we try to take the log of 0, since mathematically it doesn't really make sense. Again, we just get a warning, we don't actually get a full error. Okay, so something to keep in mind, there's a lot of universal array functions that are available to us in NumPy. And if you go to the lecture notebook for this particular lecture, we link you to this documentation page with, if you start scrolling down, you'll have a list at the bottom of all the different math operations, trigonometric functions, comparison functions, etc., that are available to you in NumPy as universal functions. So we can essentially just do NP and then do some sort of call here. So that link is available to you. However, we won't really be using too many extravagant NumPy universal function calls. What we will be using a lot are summary statistics on arrays. We're often dealing with really large data sets, and we want to perform some summary stats in order to get an idea of just the general intuition behind the data set. So we can do this. If I check out my original array, I can call things such as sum, which we've seen before, that actually just sums up every element in this array. But there's other ones such as mean, which takes the average, or I can also call things like max. Now there's other things like the variance and standard deviation, which we'll discuss further, especially when dealing with real data sets. But keep in mind, those are already all built into NumPy, so we don't actually need to calculate those out ourselves. The main thing I want to point out here is that there's the component of axes logic. So right now we've been doing everything across this one-dimensional array, so it makes sense that if we sum things up or take the mean, it takes all the elements into account. But let's go ahead and create a two-dimensional array. So I can do this by saying something like NP arrange, and then what I'm going to call here is, let's say, 0 through 25, and if I run that, I get these 25 elements, so I can reshape this to be 5 by 5, and then I get back this two-dimensional array. So let's go ahead and say array 2D is equal to NP arrange, which means the shape of this two-dimensional array is 5 by 5. Now, I could call something like sum on this, and it will sum up all those numbers. But let's imagine I actually wanted to get the sum of maybe all the rows or all the columns. How do we actually do this? Well, you'll notice that sum actually takes in an axes parameter, which means you can actually specify whether you want to perform this operation across the rows or across the columns. Keyword being across. So what I'm going to do here is say array 2D dot sum, and I'll say axis is equal to 0. And the result here is 50, 55, 60, 65, 70. So recall when I say array 2D shape, the element at index 0 is the rows. So rows is represented by axis equal to 0, which means if I were to say dot sum at axis equal to 0, it means perform this operation across the rows, which gives us this result, which is technically the sum of the columns. So that can be a little confusing for beginners. The fact that by saying axis is equal to 0, it means perform the operation across the rows. Similarly, I can say array 2D dot sum and set axes equal to 1, run that, and that'll perform the operation across the index 1 of shape, which is the columns. So it performs this operation across the columns. So keep that in mind. Axis equal to 0 says perform this operation across the rows. Axis equal to 1 says perform this operation across the columns. That can often be confusing for beginners because they kind of expect the results here to be switched. But the key word to remember is the operation across. Okay, so that's it for this lecture. We'll be using these sort of method calls and arithmetic calls later on in the course. I'll see you at the next lecture.